done T and V, we have done T and P. So the last one, what we're going to do in this video is P and V. So this one we're going to use a different ways again. For the first part we just use a du, the expression of du, but second part we are using expression of enthalpy, and for this one we're going to make use of the internal energy again, but we also going to make use of the state equation or state parameter relation, as what we have done in the chapter 2. So what we have done in the first part, where we do the relation of T and V, that del U just simply del U related to T and V. So this one we can make it relate with P and V, so similar what we have done earlier. So del U is equal to change of pressure, the change of internal energy due to the change of pressure, because we're going to have only P and V here. So this one should be at constant volume, change of pressure. So this is change of internal energy due to the change of volume. So this time is constant pressure. So this is volume. So the other one, because the reason we are doing this, we are using this because we want to have dP and dV. So this is quite convenient, but we will just make use of the relation here to have another identity, because we just make use of the relation to somehow give us another mathematical expression that we can make use later on, because this is only this is expression that this is true, and then it's only related to all of this system properties. Okay, so we can so instead of doing like this, we can have another set of this, because here we have a whole bunch of this value. So okay, so another one we can also rewrite like this. If we put it this way, so we have another set. We can have another set of this, which just to have everything included within this du. So we can have another set of du with removing P. In this case, we will put the change of internal energies, the change of temperature, plus the same change of energy, change of volume. So this is a constant volume, so this is a constant temperature, change of volumes. Okay, but if you look at here, we have two ways of expression, but we don't have the same P and V. So one way we can just write down like this, another way we can write down like this, but then we can even do many ways. Actually, we can have another way. So this T and V, we can also could make it T and P, either way. So we just want to try to make a comparison of du with only that relate P and V. So in this case, we try to remove this del T instead. So how could we do that? Is by having del T is equivalent to, this is state equation. So change of temperature due to the change of pressure. So this one is constant volume, change of pressure, plus change of temperature due to the change of volume at constant pressure. So this is volume. So we already have dt. Then if I were to put here, then we only will have dp and dv. So I can rewrite this equation into another equation, which is del u is equivalent to del u del t, this whole thing, and plus the remaining we are putting this value there, so we already have everything here written. So the remaining is del u del v del v. Okay, so I just try to rearrange, put it all the dv together and dp together. So this one is, I forgot to write that this one a constant volume. So if I were to multiply this will give you del u del t constant volume del t del p at constant volume dp, and then this one multiply with this plus del u del t constant v del t del v at constant p, and this is del v. Then I can factorize the del v. So this one multiply with this, we get this, and then multiply dv, then I factorize dv, and then this one will be this whole thing become dv. So what we have here, so this is another expression with this. So if I were to bring this one closely, what we can have here is that we can make a comparison, because both of these are true. Both of these are true. Then we can make use of this by making a comparison. Such way I can make it in this way, that del u del p at constant volume is equivalent to del u del t constant volume del t del p at constant volume. So if you look at here, we have an energy, and then we have all the state parameters. So one of the state method parameters is being constant all the way through both sides, and then the other one is related to. So here we can make another identity in such way. If I were to make du become dw, so the dp become dx, and then this one become y. So this is the same with this. So this is w, t is a different one, so I should make use of z, and this is the same y, and then this t is t is z, and dp is dx. This is y. So we have another identity. So another one, if we make a comparison with this one and this, so we will have that del u equal to del V at constant pressure will equivalent to del U del T V del T del V P plus del U del V T. Okay, so if you look at here again, what we have the all state parameter. We have U, V, T, and P. So again, we can make this become another identity for us. So it doesn't matter what you label, as long as it's consistent. You just have the dimension to be consistent. So if you look at here, P, we don't have any component P here, and T also we don't have any component. So and this one have to be consistent with this, but it have different constant value. Okay, and this one share with this, so I can rewrite this one to become again dw dx. So this is y, so this is dw again, so this is another one, this is dz. So what we have, so dz at constant x, so t is z x, and then p is y plus dw dx del x. So t is z. So if you look at here, it will be x, y, z, and then this is y. So you can just remember that it all the one of the components should be constant in each any of this case, but this cannot be constant with this either of these two values, and then the one that constant with this shouldn't have any component with this value, but then if you look to this component, it's always back to this w dx. So wz del z del x, so if you cancel del z both together, you still get w del x. So this is also the same. So you have to figure out this one. So we get another identity. So these two will be useful to us later on. Okay, let's do one example given in the lecture note. So if we are dealing with improving del u del p, what is the value for del u del p at constant volume? To show that this expression is equivalent to this. So we can make use of this expression. Remember, we can also have this expression to be so you already know this is del u del t, so we can make use of this identity. So we just rewrite down del u del p v, or maybe it can also be the other way around. We can just show, because we already know what is this value. So cv cv is del u del t at constant volume multiplied by del t del p at constant volume. So since that based on this identity, that dw dz y dz del z del x at constant y equal to del w del x. constant y. So from here you can have that this will be equivalent to del u del p at constant v. So that's one way to do it. Another way to do it, you can just using the other way around, because you already know here. So since that del p at v, then we obviously using this. So again, the dw is for del w, del z is for because this is x, so this is not del p. So it be the other values. We have u, p, and v, and then another one is t. So this one w x y. So this w x y, and then the one that is with z. Z is something else beside u, p, and v, which is t. So at constant, so this is the same constant. So this one should be also the same constant. So the second one is del z. So what is del z is also dt here. So del x is comparison to del p. So this is del p. So at constant, so everything is y. So this also everything is v. And then from here you know that you can just clear that, since that cv equal to del u del t at constant volume, then you can replace this with cv, and thus prove the relation.